Hello friends, this is Praveen Kumar from Hyderabad, teaching EDC and Analog Electronics in Gate Revolution Chandigarh. Here I would like to discuss a small topic in analog electronics, that is biasing. Before that, I would like to give the importance of EDC and analog electronics in gate. For electronics and communication students, the weightage of EDC and analog electronics is minimum 20 marks, maximum 25 marks if we take the average from 1984 to 2018. Coming to the electrical students, the weightage of analog electronics is minimum 7 marks, maximum 9 marks. For telecommunication and instrumentation students, analog electronics weightage minimum 6 marks, maximum 8 marks. Here, my question, what is transistor? An electronic component which can transfer the signal from one resistance region to other resistance region is called as transistor. It is basically two types, unipolar, second one is bipolar. In unipolar transistor, current flows only because of one type of the charge carrier, either electron or hole participates in conduction. We have two transistors as examples. One is UJT, unijunction transistor. Second one is field effect transistor, FET. FET is three types: JFET, junction field effect transistor; MSFET, metal semiconductor field effect transistor; MOSFET, metal oxide semiconductor field effect transistor. Coming to the metal oxide semiconductor field effect transistor, it is designed in two ways. Based on the channel availability, we are categorizing in two types. One is enhancement mask transistor, second one is the depletion mask transistor. Enhancement mask transistor simply acts as the switch, digital switch, whereas depletion mask transistor using as a switch, carrier, at the same time it is used to design ultimate digital circuits and FPGA CPLD circuits. Now coming to the second transistor, bipolar transistor. In bipolar transistor, current flows because of both the carriers at a time, means electrons and holes are participate in the conduction process. Best example is BJT. In bipolar junction transistor, if you observe the terminals emitter, base, collector. Between emitter and base, we have one junction called as the emitter base junction. Between base and collector, we have one more junction called as the base to collector junction. Based on the applied DC voltage to the emitter junction and collector junction, we can operate transistor or BJT in four regions. First one is saturation region. In saturation region, emitter junction is forward biased and the collector junction is forward biased. In this particular region, transistor acts as on switch. In cutoff region, second region is cutoff region. In cutoff region, emitter junction is reverse biased and collector junction is reverse biased. In this region, transistor, that is BJT, acts as off switch. Third region is active region. In active region, emitter junction is forward biased and collector junction is reverse biased. In this region, BJT acts as amplifier, which can increases the amplitude of input signal. Last region is reverse or inverse active region. In inverse active region, emitter junction is reverse biased and the collector junction is forward biased. In this region, transistor or BJT acts as attenuator, which decreases the amplitude of given input. Out of four regions, third region, active region is most important, because in this region, with use of BJT, we can design almost 50 amplifier circuits like small signal amplifiers, large signal amplifiers, low frequency amplifiers, high frequency amplifiers, single stage amplifiers, multi-stage amplifiers, negative feedback amplifiers, positive feedback amplifiers, differential amplifiers, multi-vibrators. Like this, we can design many BJT circuits, more than 50 circuits we can design with use of BJT in this active region. So in active region, we have to give the external DC voltage for emitter junction as well as collector junction. With biasing, transistor or BJT acts as the amplifier. If you take BC107 or BC547 in emitter junction, active region, emitter junction is forward biased, collector junction is reverse biased. Because of this particular biasing, BJT acts as perfect amplifier. It acts as amplifier. After manufacturer prepare the BJT, if we use this particular BJT BC107 or 547 for the amplification, immediately we will get output as the exact replica of the input. Means transistor provide best amplification without any replica, but we are using biasing circuits, we are using stabilization circuits, we are using compensation circuits, we are taking some precautions to amplify the signal without any distortion with high stability. Why we have to bias the circuits? This is my concept. Why we have to bias the circuits? My simple answer. With use of DC voltages which are connecting in forward bias emitter junction, reverse bias collector junction, transistor is providing the amplification, but after some time there is a possibility of changing the amplification functionality. Why amplification functionality will change or output will distort? Here we have technical reason. What is that reason? I will explain. We are connecting DC voltage to the emitter junction, collector junction. If we apply constant DC voltage to the any electrical or electronic component, obviously it dissipates some heat. I will give the real-time example. If we charge the mobile for 1 hour, after 1 hour, if we touch the mobile, definitely we are sensing heat. Means because of 3 volts DC voltage, mobile is dissipating the heat. Then for amplification purpose, we are using 12 volts DC or 15 volts DC. When compared with mobile charging DC voltage, this amplification DC voltage is very high. Then obviously because of 12 volts DC voltage or 15 volts DC voltage, heat is dissipating at emitter junction as well as collector junction. The dissipated heat is affecting 3 parameters. One is forward bias voltage VBE. One is forward bias voltage VBE. How temperature affect this forward bias voltage VBE? As continuously applying the DC voltage to the emitter junction, the temperature increases across the emitter junction and is affecting the base to emitter voltage. How it affects? It affects base to emitter voltage with this relation, minus 2.5 millivolts per degree centigrade. For every 1 degree rise in temperature, forward bias voltage VBA decreases by 2.5 millivolts. If voltage decreases or VBA decreases, what happens? We have the equation for base current IB, that is VBB minus VBE by RB in forward bias condition. VBB, RB, both are constants. If VB is decreasing, automatically IB increases. If IB increases, then what is the effect on IC? We have the equation IC is equal to beta IB plus 1 plus beta times of IC naught. As IB is increasing, automatically collector current IC increases. As IC increases, VCE changes, operating point shifts from the center of the DC load line or center of the active region. For amplification purpose, operating point should be always at the center of DC load line or center of active region. Now because of changing of IC or due to the changing of EC, operating point shifts. If the operating point shifts, automatically output distorts and the stability decreases. So to increase the stability or to generate output as the exact replica of the input, we have to use biasing circuits, fixed bias, collector to base bias, emitter resistance bias and self bias. What is the second reason? Second parameter is reverse saturation current IC naught. Reverse saturation current IC naught. Whenever we apply DC voltage to the collector junction in reverse bias, because of the reverse bias voltage at collector junction, temperature increases. As temperature increases, IC naught increases. How it is increasing? For every 1 degree rise in temperature, it is increased by 7%, and for every 10 degrees rise in temperature, it doubles. It doubles. With the equation of IC naught 2 is equal to IC naught 1 into 2 power T2 minus T1 by 10. As IC naught is increasing, from this equation IC increases. As IC is increasing, VC decreases, operating point shifts from the center of the DC load line or center of the active region. If the operating point shifts, automatically output distorts. As output is distorting, stability starts to decrease. Now, to increase the stability or to generate output as the exact replica of the input, we have to use the biasing circuits. And the last parameter is the beta, current gain beta. How it affects the IC and VC values. If you observe this equation, as beta is changing, IC changes. If beta is increasing, IC increases. As beta is decreasing, IC decreases. As IC is changing, VC changes. As VC and IC changes, operating point shifts, output distorts, stability decreases. My question, how beta changes with respect to temperature? As temperature is increasing, VB decreases, IC increases. As temperature is increasing, IC not increases, IC increases. Means because of the changing of temperature at emitter junction and collector junction, IC is increasing. As IC increases, what is the effect on beta? Beta is equal to IC by IB. As it is increasing, beta increases. As beta increases, again IC increases. As the IC is increasing, VC decreases, operating point shifts, output distorts. Thus, these three parameters which are depending on the temperature affects the amplification process. That is the reason why for every amplifier circuit we have to use the biasing circuits in designing process, which are fixed bias, collector to base bias, emitter resistance bias, and self bias or voltage divider bias. So in analog electronics, in design of BJT amplifiers, biasing is very important. Biasing concept is very essential. I would like to raise the two questions, only two questions. One question: if temperature is affecting the IC naught VBA beta, then by using the biasing circuits we can stable the operating point. Suppose if temperature based components are trying to change the operating point positions, then what we have to do in amplification process? Obviously we have the ultimate answer for this one, sir. If temperature based components are affecting the amplification process, in that particular case we have to use the compensation techniques. What are the compensation techniques we have? One is diode compensation, second one is thermistor compensation, and third one is transistor compensation. You may raise the question, if those techniques also unable to stable the operating point, in that particular case we have to take some precautions. We have the ultimate precautions to control the amplification process, to stable the operating points. Those we can explain with use of the concept of thermal runaway. If possible, in regular classes I will teach you thermal runaway with the proofs and equations. I wish you all the best. Thank you.